Hello students, welcome to Optimization Method for Civil Engineering, Week 0. I am Antriksh Srivastava, PhD scholar from IIT Madras. Today we will be discussing a topic which is very important when it comes to linear algebra and every field. So how to calculate eigenvalue and eigenvector for a matrix. So let's first understand geometrically what does eigenvector means. So A is a matrix of order n by n. Then vector x is, so we all are aware of this definition that a vector x which satisfies this relation is the eigenvector for a matrix A. But what does that physically mean, geometrically mean? So it means that if we multiply the matrix A with the vector x, then the resultant should be a multiplication of it should be similar to the multiplication of that vector x, a scalar multiplication. So let's understand this geometrically. So let's say if we have a vector two, we have two vectors, vector x and vector y. So then we perform this matrix multiplication on both the vectors. The resultant vector of those two multiplications is ay is in some other direction, whereas the ax is just elongated version of x or shortened version of x in the parallel to the x. So in this case, you can understand that this x vector is an eigenvector for matrix A, whereas the y vector is not an eigenvector for the matrix A. So from this figure, we see that vector x is an eigenvector, but y is not, and the matrix multiplication Ax is in the same direction as vector x, and the length, the multiplicative factor with which the length of the vector is increased is called the eigenvalue for that particular eigenvector. Okay, now coming to the algebraic aspect. So we have the same equation ax is equal to lambda x. We bring the lambda over to the left hand side, and so to subtract a scalar from a vector, we need to multiply with the identity matrix. So we perform that. Now we have let's say a matrix B is equal to A minus lambda I, and then B into x is equal to 0. So we want to find out vector x. So x should not be equal to 0. Otherwise, there is no point of the above equation, right? Now, for this to be true, x it has to be in the null space of V. So what is null space? Null space of a matrix A consists of all non-zero vectors B such that A into B is 0. Okay, now how do we solve? How do we get this eigenvector and eigenvalues? Now, from the multiplicative property of the determinant, we know that determinant of A into B matrix is the multiplication of determinant of A and determinant of B. Now, that means this above expression A minus lambda I into x is equal to 0. That means either the determinant of A minus lambda I or the determinant of or the vector x has to be 0. But since we already discussed that the vector x cannot be 0, that means we get an expression or equation that determinant of A minus lambda I has to be 0. So, and which is also known as characteristics equation. Now, when you simplify this expression, as we have all learnt in our school days or even in college first year, so we'll get a polynomial in lambda, and the root of these polynomials is will give us the eigenvalues. So that's how we get the eigenvalues, and from these eigenvalues we can just solve the homogeneous equation that we will get by putting each of the eigenvalues one by one into this expression, and we can get the eigenvectors. So now here are some of the forever rules or some must remember rules for the eigenvalues and eigenvector. Sum of eigenvalues is the sum of diagonal elements of a matrix, and that is called trace. Product of eigenvalues is the determinant of matrix. All eigenvectors are linearly independent. So if you have a eigenvector, you cannot express that eigenvector in form of by linear by a scalar multiplication of any other set of eigenvectors for the same matrix. So simply writing xi cannot be equal to kxj for I not equal to j. So this I have written for if there are only two eigenvectors. If there are multiple, then you can just write plus x plus k2x k and plus k3 x alpha and so on. You can write that, but that won't be equal to, we won't be able to write the any eigenvector in by a linear combination of the other eigenvectors. Okay. And some important rule that may be useful for competitive examinations is that the matrix also satisfies the characteristic equation. So we have seen that this is the characteristic equation that we use to determine the eigenvalues. So if we just replace this lambda by this matrix itself, then we will see that the matrix also satisfies this characteristic equation. This can be useful in identifying the inverse, or if in some examinations some complex matrix multiplication to the power has given. So it is a good idea to check whether that in somehow is related to the characteristic equation for that matrix. So now we know what are eigenvalues and eigenvectors. Let's just take an example to calculate that. If you want to pause the video and calculate, you can do that now, but I will start discussing the solution. Okay, so this is the matrix we have 2 1 2 2. Now to get the eigenvalues, we know we have to identify the determinant of A minus lambda I. So A minus lambda I will subtract the lambda from the diagonal element. So we get this matrix, and the determinant, when we put the determinant of this matrix equal to 0, we get the two lambdas as 2 plus minus root 2. Now let's calculate the eigenvector for the first lambda, that is 2 plus root 2. So when we substitute this lambda into this expression, v and a b being the elements of the eigenvector, so we get this homogeneous equation. Now to let's reduce this, we have to reduce this homogeneous equation into echelon form. So you can do it without this row reduction also, but I prefer to do that. And it also helps in a complex three or four order matrix. It helps us easily solve these expressions. So you perform this row operation, that is row 2 is equal to row 2 plus 2 times root 2 times row 1, and we make the lowermost row 0. And then to convert it into a proper row echelon form, we have to divide the first row by minus root 2. So this also is simpler to understand, but since I said row echelon form, so I'll be converting. We have to divide this by minus root 2. So then we get this expression. So x1 again is a and b in a column vector. So once you look at this expression, we see that will be 1 and b is going to be root 2. You can just simply put one value for a, and then you can get the value for b. So this is our eigenvector for the eigenvalue 2 plus root 2. Similarly, you can do for the 2 minus root 2 eigenvalue, we will get 1 minus root under 2 eigenvector. Now here also we can emphasize on the fact that these two eigenvectors, you cannot write one in the form of other. So let's say if you want to uh, change this to minus root 2 by multiplying minus 1, then this first entry also will become minus 1. So it's since they two are linearly independent, so the eigenvectors will be linearly independent. So we can again check the property with this example. Now, so this is an example that I had taken from Khan Academy, and I have solved it using Roy-Leon deformation. So we can, I will pause now and okay. So now let's try to solve this. I hope you have solved. So we'll not go through all the details. Just we are. This is the characteristic equation. When you solve for the determinant of a minus lambda I and you simplify it, you will get this characteristic equation. Now the here what we see is the eigenvalues are the three is being repeated two times, and minus three is one of the eigenvalues. Now here's one interesting thing to note. Sometimes when eigenvalues repeat themselves, then they may have only one independent eigenvector. But there are some cases, and there are many cases in fact, when one eigenvalue can have multiple independent eigenvectors. So since you see that there are only two unique eigenvalues for this particular matrix, you cannot just simply say that this particular matrix has only two linearly independent eigenvectors. There can be three also, and that's what we will see now. So let's find out the eigenvector for the eigenvalue 3. Then we put the lambda is equal to 3 into a minus lambda I format, and we get a new matrix. And then we have this homogeneous equation that we will solve. So we can again reduce this equation into row-echelon format by performing these row operations. That is, R3 is equal to R3 plus R2. So R3 will become 0. R2, after that, R2 is equal to 2 times R2 plus R1. Then R1 becomes 0. And then to convert it into a proper row-echelon form, we'll just divide the R1 by minus 4. And here's the interesting part that I was talking about, that this lambda 3 has, we can clearly see that we can write two independent eigenvectors for this particular lambda. So one is 1 1 1. So you can just cross check this thing by putting this x1 here and then doing the matrix multiplication. So what we see is minus 4 plus 2 is 0, and similarly for the lower two rows also it satisfies the expression. Similarly x2 also we can check here. So minus 4 plus 2 into 0 and plus 2 into 2. So minus 4 plus 4 is 0. And similarly, row 2 and row 3 will satisfy this criteria. Now, for eigenvalue minus 3, we again put the lambda into the a minus lambda I, and we get this matrix, and we have a homogeneous expression. We will solve it by converting this A matrix into a reduced row echelon format. How do we do? We perform these row operations one by one, and we get the reduced form as this particular form. And then from this, it is easy to identify. You can just take any value of x, the third element. I have taken 1, and then from that we get the value of second element by solving this expression, that is 1, and by putting these two values into the first, we can get the value complete eigenvector x3. So again you can see that these three eigenvectors, that is x1 and x2 x3, are linearly independent. So we can just check here. So let me just copy these things. So we have x1, x2, x3, the three eigenvectors here. And let's just check if we can identify any trick to get them to be linearly, just to cross check. So we see here, if we were to just subtract So we have to get the 0 on the second. So we have to subtract this or add this. So if we do that, what do we get? So let's subtract x3 from x1. So it will be 3. Let me just write here. We just insert a text block and just write here. So 1 minus minus 2 is 3, comma, then a 0, and then 1 minus 1, 0. So we see we are not able to express this into x2. A more accurate way to check would be to put this into put these three column vectors into a matrix, a 3 by 3 matrix, and then to calculate the determinant. So if the determinant of a matrix is 0, then that means there is a dependency between the rows or the columns. So let's do that. In fact, so I have here my MATLAB open. So I'll do CLC. So let's make a vector A, and let's put these values into them. Let me just copy this. Let's do, sorry, so for it to be in a column, we have to give semicolon. So this is our vector. So probably it is asking me to write into a different format. So let's do that. So we have our A vector here. So this is what we had. One first eigen vector as minus 2, 1, 1, second one, 1, 1, and third 1, 0, 2. Now let's calculate the determinant of A. So determinant comes out to be non-zero. That means these three vectors are linearly independent. So here we solidify our point, our argument that one eigen value can have two or multiple, in case of n order matrix, can have multiple independent eigenvectors. So I hope this was helpful. So one point I forgot to mention is that, see, the reason why we do row echelon format is very simple. We have already discussed that to identify this the lambda that we obtain by solving this expression is going to make a matrix A minus lambda I, which is singular. The determinant of that matrix has to be 0, and in that case, always, every time you will get a row if you are doing a row echelon reduction, or a column if you are doing column reduction. One, at least one of these rows will be complete 0. So this helps you also to check whether you are in the correct path in the end or not. So for lambda is equal to 3, we got two of those rows 0, and for lambda is equal to minus 3, we got only one row 0. So this kind of a rough check, but it's better to follow this approach while solving. So that's all for this week 0 session. I hope you learned something about eigenvalue or eigenvector, and we'll see you in the week 1 session. Thank you.